Let's talk about Newton's method. Newton's method is a kind of computer style way, programming style way of finding zeros, and it's named after Sir Isaac Newton. If we want a zero of a function, then what we need to do is we need to find a number of values of this particular formula that will end up being the same as each other, and that'll make a good approximation. So a zero of a function is approximately equal to this, what we're going to call x sub n plus 1, and x sub n plus 1 is equal to x sub n, these are subscripts, minus f of x sub n over f prime of x sub n. Now the subscripts are just like 1s and 2s and 3s, and so if we start with 1 for n, then this one will stand for 2. And so x sub 2 is related to x sub 1. And then if we put x sub 2 in here, it'll be related to x sub 3, and so forth. So that's kind of the idea. It's called an iterative procedure. What I thought we would do is find the zero of f of x, and there are two of these, but f of x equals x squared minus 2. Now you know from algebra that the answer to that is square root of 2 or minus square root of 2. So we could try that, but we're going to try this process instead. Now what I'm going to do is I'm going to set up a value tree, and I'm going to put x sub n right here and x sub n plus 1 right here. Normally we put x here and y here. I'm going to treat it that way on the calculator. And usually we've got to have a starting value. Now sometimes that's up to you, sometimes that's given. I'm going to choose x sub 1 is equal to 2. I'm just going to choose that. So I'm going to put 2 in here, okay? Now, f prime of x is 2x, so our formula is going to be this. And it's specific for this formula, this function, but we're going to say x sub n plus 1 is equal to x sub n minus f of x sub n, that's x squared, minus 2 over the derivative, which is 2x. I've got to put the subs in there. So there we go. All right, so what I'm going to do is I'm going to put this in the calculator. Now I already have it in this calculator, so we'll just deal with that. This calculator has the function put in, or the formula for this. That's not really the function, it's the formula that we're using. What I'm also going to do is I'm going to use the table feature of the calculator. So let's go to the table, and I'm going to start out by putting our starting value of 2 in here. So let me do that. Put 2 in there, and I get 1.5. Okay, so 2, 1.5. Now the reason this is called iterative is because then I take 1.5 and I stick it in. So when I stick 1.5 in, I get 1.4167. Now there are a lot more digits on this. If you look here, right down here, you can see it's got a lot more digits. But I'm just trying to look at the ones that I have. So let me go over to x again. Notice I've got the table set on ask, not on auto, the x part. So I need to put 1.4167, 1.4167, and that's going to give me 1.4142. So 1.4167 gives me 1.4142. Then I put that in, 1.4142, and notice it's the same. So 1.4142, 1.4142. Once we get agreement on like 3 or 4 decimal places, we usually say, hey, you know, that's a pretty good estimate. And if you go into your calculator and find the square root of 2 It's not too far from there. So that's a good estimate. Now, if you want to find the negative square root of 2, you'd have to start somewhere closer to negative 2. And it should eventually come out. This only took about 3 or 4 iterations to get there. Depends on how close you are and what number you choose, how many iterations it's going to take. Each one of these times that we put a number in is an iteration. Once in a while this doesn't work, and if it doesn't work, you can try another value, or once in a while it just flat doesn't work. It just kind of jumps all over the place, and it has to do with the fact that sometimes this denominator, which is the derivative, just it changes values a whole lot depending on what's subtracted from it. And it's based on the tangent, of course, because it's a derivative. So this doesn't work for everything, but it's kind of a neat process, and you can use your calculator to make some good estimates.